What the remainder of this talk is about is the lightweight multitasking executive that I use in order to run multiple tasks concurrently. So I'll start this off and wake up Inbot over here. Wake up Inbot. Any time now. And what I'm going to do here, I want to get Inbot to tell us a little bit about the multitasking that it's running. So, everybody read that? So, this is a dump and just a current snapshot. And what it tells us is that we're running 13 tasks and that they use 1935 ints off the heap in order to run those tasks. And then we have a process ID for each one, which is the first column. And we have a name for each one, which is just arbitrary. And then the size of the stack that was assigned to this task, and then the amount of stack size that it actually used. And I want to go over these in detail, but I want to get one more dump here, if it will do it. This has similar information. Oh, no, it doesn't.
Uh-oh, it doesn't look like something's an issue.
No, it's because I didn't turn it on. All right. So he's going to get picky about it. Still garbage? Yeah. Okay. It's actually doing all this out of a little log that it builds internally, so we'll let him build the log here for a few seconds. Oh, if you set off that little center alarm, that's what sets off the audio. When I first showed that to the group, I was told that I had trivialized all my hard work. Okay, that should be enough.
I like it when it comes to this in my office. I have to do.
It tattles. There we go. So let's go over these. In this case, what it's told us is that we're using a total, for that little runaround there, we only use 16% of the available CPU cycles. So we got lots left over, even in this old, long-in-the-tooth, slow processor. And that the idle time, which I specify in hertz, was about 7.8 kilohertz. We'll come back to that number in a minute. For each task, and we'll go over them here just briefly so you can see what the robot's doing. The first one's called the LCD queue. It was assigned PID number 1 when it was started up. It's used 1.88% of the CPU cycles, and its average time that it runs is 0.933 milliseconds. What that task does is it hangs on a semaphore waiting for somebody to write into a queue. And when they write into a queue, it reads out of that queue, and it writes to this LCD display. So that's what's writing right now to that display. The second task is that A to D converter and filter that we already looked at. And you can see that it's taking 0.9%. Wow. Well, what does that mean? Come back. Who failed? Didn't it just say somebody failed? Lost my port. Well, bummer. However, because I thought that might happen. All right. The second one's the A to D converter. The third one, I run a long-term running average of the battery voltage. Since the battery voltage is kind of all over the place when you're actually running, to actually know its level, you need an average. The third one, you can say, actually uses almost 3% of the processor cycles, and that's the thing that handles the input and output. It reads these buttons, it writes to the display, it writes to the serial port, it's the thing that's writing here, and it can also do some other internal logging. The one called METR is the thing that actually balances the robot. You can see that it's using most of the processor time. It says it uses up about 7%, 6 or 7% of the processor time. The sensors are all the sensors that are running. That is the ping sensors, everything, all of the sensors on the robot. And that takes a small amount of time, actually much less than you would expect. There's a trace that's running, that's pin number 7, which is the thing that's calculating these statistics. Then the ping itself we looked at. That's the thing running the 2 sonar pings with the 20 millisecond voice in between. The little silly sounds you've heard are generated by task number 10, which is the Anderson 1-bit FM synthesizer. And it's driven by task number 9, which is called the voice. Voice, you hand it syllables, and it drives the synthesizer. It also reads from a cue. The 11th one it says is heartbeat, and this is something that I run on most of my robots. If you look, I don't know if you can see, down inside there's a green LED right back in here, flashing on and off. That just goes on and off once a second and tells me that the system is alive. And the last one is the Null Task. The Null Task is started up by the system at startup, and it does nothing. It runs constantly. All it really does is it increments a counter. So you can use that counter to tell you how many times you've made it around the loop, and that was that idle number. So what idle says is that in the last second, 8,634 times, null executed. And that number is actually a really useful number to know what the system is doing. For example, if you have a task that's waiting on a pin, an I/O pin, that number tells you how often you were sampling that pin. So in this case, you're sampling it at 8.6 kilohertz, something like that. Sir?
Why is it PID number 13 instead of number 12?
Good man. Number 12 was an initialization task. So it started up and it initialized things like the IMU and the LCD display, which take a while. Those take a while to come up. And when they are all initialized, it sets a flag that says everybody's up and running, and it terminates itself. So that's why it's gone. Any other questions about that? Before I leap forward. Just wanted to kind of briefly show what's running here.
Are you going to map those to the different levels of the code you talked about previously?
Yes.
Okay.
When the this is what we've got 12 tasks running here. There's a bunch that aren't running here. Wall following, navigation. There's a lot of other tasks that could be running. In particular, when we run navigation, this processor has no hardware floating point. So it has to do all the floating point in software. And that includes sines and cosines and arctangents and everything. and that means they're very slow. So when we turn those on, which I'll do here in a minute, you'll see that we're actually eating up a whole lot more processor time when we're actually doing something rather than just wandering around and bouncing off the walls. So what I want to do here is describe briefly this cooperative tasker that I use. And what I'm trying to do is encourage you guys to organize your software in the same kind of way, whether you use my implementation or one of the many other free and commercial ones that we talked about. For this, again, we ported this software. I've been running it for years on my 68332. Ron helped me get a port running on the ARM Teensy. So we got it running on this guy. And Mark Sims got it running on AVR. And we've done a bunch of benchmarks on those, which we can use for comparison between the two. I will leap ahead and spoil my thunder by saying that this number, 8 kilohertz on this processor, that number is about 60 kilohertz on the AVR. It's at 2.5 megahertz on the ARM. So just to give you a feel, you're going around that loop. That if you ran the same loop 2.5 million times on the ARM and 8,000 times on the, we've come a long way. So, okay, so let's, as I say, briefly here, just look at the one that I use, and this should be, any that you use should have the same functions with it. A cooperative task in this context is just a standard C subroutine. There's nothing special about it. It just looks like a standard C subroutine. It returns void. That means we don't return anything. In point of fact, it never exits, so there's nothing to return. And it accepts a single argument, which I say here is A size, argument size. That argument needs to be controlled by how big your timer was. Remember we talked about 32 and 64-bit timers. So If it's a 32-bit timer, you can use a 32-bit argument. If it's a 64-bit timer, you probably need to use a 64-bit argument. It's just a single argument, but you can cast that to a pointer. Those of you who are C aficionados, if you need to hand in more than one argument, you can just use a pointer to hand in multiple arguments. The tasks are arranged in a circular linked list. So for those of you who don't know, a linked list is just a list in which every item in the list, one of the items, is a pointer to the next list, and a pointer to the next list. So if you look at the arrangement here of the drawing, we have an endless loop here that points to the next one, he points to the next one, he points to the next one, and the last one points back to the first one. So it's a circular linked list. This is round robin execution, which means each task executes every time around the loop. That's not strictly true, but for our purposes, it is. And tasks actually defer, we use that term, defer to the next task in the in the linked list voluntarily. So this is a cooperative multitasker. That is, the tasks themselves have got to voluntarily release control in order for another task to run. That's to compare it to what would be called a preemptive multitasker, in which you use interrupts to actually just, whatever task is running, you just halt it dead and put it away and start the new tasks. This is not preemptive, this is cooperative. And that means a couple of things. The tasks themselves, the way they defer is they call the subroutine named, appropriately enough, defer. And when they call that subroutine, the task that calls it is stacked and put away, and the next task is fetched. That task is executed. So even from the point of view of any particular routine, we just called this routine defer, and it returned. And then I went about my business. The routine doesn't know that when I call that routine, everybody else in the linked list executed before it got back to me. It's kind of clever how it works, because if you think about what you're doing, you're calling defer, but in the middle of defer, you're swapping the task frame. So you're not returning to the task that called you. You're returning to the task that called the next defer. So our execution, I could draw it with my finger. Our execution would look like this. We're going to come down here until we hit defer. There we stack that task, and we return from this defer. And we loop and call defer and return from this defer, and so forth, continuously around the loop. Again, they're not really running simultaneously, right? They're running in sequence. It's just for us, they appear to be running simultaneously.
So do you store the state of each task or certain variables of each task? Is that why you...
Say again.
When you, just before you defer, do you save off the state of that
Defer
task?
does that.
Defer does that. Okay.
Defer does that. What defer actually does, and we can look at the code if you like, what defer actually does is it runs around that linked list looking for a task that's ready to run. Each task has a state, and if that state says I'm ready to run, then at that point, he stores the old and loads in the new one. If he makes it all the way around the linked list and there's nobody that wants to run, which is possible, then he doesn't actually store, he just returns from that subject. He really does just return from the subject.
Your computer batteries now.
So, Dave,
Is this
does it run
power
idle? I thought you had an idle task.
I think the power strip might be on. Try it.
Yeah, there we go, thank you. Wonder if that's why I lost my port.
We had a question on the back, Dave. I don't know if you heard.
Rich,
So you're counting the idle task as not really being special there. You're
All-
saying it never,
all
runs
the-
to the end and comes back. It should always hit the idle task.
it'll always hit the idle task, and the idle task runs every time around. The only reason it's there, actually it's there for two reasons. First of all, you have to have at least one task. So the idle task guarantees that you have at least one. And secondly, it allows you to do this counting of the loop cycles. Any other task could do that, but only if they ran every time around the loop. If they didn't run every time around the loop, then that number wouldn't be useful. So, and there are ways that they might not run. So I think that's enough. They're cooperative tasks. That is, they have to voluntarily turn over control. The task has complete control over the processor, interrupts everything until it releases control voluntarily. And interrupts themselves are not affected. That is, we're not using interrupts to drive the system. So if you're using interrupts to read I/O or whatever, this doesn't affect that. The only interrupt we really use is we use that sys clock. And there's a lot of ways to derive that. I believe that AVR, there's a subroutine call that'll return you microseconds since the system was booted.
How does this run better than the interrupt type programming?
It's not better, it's just different.
It's different,
Yeah,
okay.
as I say, and on this robot, all three of those levels are running. So we have finite state machines, and we have multitasking, and we have the interrupt levels. They're all running, so different ones are suitable for different types of tasks. Writing your robot code in this way makes it real easy to maintain and change. Because you can go in and change this task, and it doesn't really affect this task over here, which is one of the big problems when your system gets large. You start having interactions,
Right.
and this is a good way to separate those, to isolate.
I have a question.
Sir.
So there are many different kind of commercial and non-commercial free multitasking things like this. Some of them do offer preemptive multitasking.
Some
What
of
are
them.
your thoughts on using that versus cooperative multitasking for robotics?
I will save that discussion till the end.
Okay.
All right. And there's some good ways to do that. There's some real good ways to do that. The reason that I do it the way I do it, part of it is historical, but this is a very, very small. This is just a few hundred lines of code. And we can run it on lots of different processors. Some of the others that I've looked at are really nice. They're very nice. But for my purposes, they offer lots and lots of things that I never use and which take up lots of space. For my own use, what I've really found is that if you have delays and semaphores, you pretty much got everything you need for a robot.
Yeah.
I should say everything I think I need for a robot.
Yeah, it's trying to use a sledgehammer when an attack hammer will do.
Exactly. Well said. So,
Hey,
Richard.
I worked one job where we had a religious fight about preemptive, non-preemptive.
I can imagine.
And the non-preemptive people were saying, well, if you're a good programmer, you know when to yield. We call it yield in that operating system. And if you're not, well, then you should be shot on sight and kicked back. But we lost the argument in the preemptive people. One, because it's safer, because what if you make a mistake? What's the argument?
Well,
Yeah.
there are.
Because if you go the other route, all the good programmers will end up in jail for shooting all the time.
Okay, enough. Yes, that's right.
Doesn't C++ give you some of the features that your tasker or whatever you want to call it?
It does,
provides
or it can isolate so that each instance of an object has its own variables and so forth. In terms of getting them to run concurrently, that's still another task. But Ray, there are lots of ways of doing this.
Yeah.
I'm really just describing the way I do it. But what I would like is that if you take these ideas away conceptually, then you can apply them with lots of different tools, whatever the tools are. Okay, in my case, the tasks can have two different forms. And those really are tasks that never exit, like what we've been talking about, and tasks that do exit. So a task that never exits, here I said, here's a sample. We return void, we take an A-size argument, do whatever initialization, and then do this endless loop that somewhere in the loop calls this defer call. And those of you who program with Arduino IDE, this probably looks familiar to you. You have a setup and you have a loop. And so this allows you to kind of think about it in the same way. The other type of task, that would be a task which exits. Since we're in this round-robin loop, you can't just say return or exit because you're still in the loop. You actually have to be removed from the loop. And there's a command here called terminate, which will do that. So, for example, the question I was asked earlier about what happened to task 12. Task 12 went through and did all this initialization, and when it was done with all that initialization, it called terminate. And terminate pulls it out of the linked list, frees its memory, it's gone. It's no more. For the most part, you don't do that very much. My navigation tasks, when they find a goal, they terminate. So you actually have to start up another task if you want to go to another goal. But for the most part, everything is endless loops, like the first example. So, okay, you don't really call defer directly, even though that's what I had. You can, if you want to. But more commonly, it's invoked by a call to either wait for a certain period of time or to suspend on a semaphore. And when you write the code, that's what you'll actually get. Sometimes you might call defer. If you're waiting in a real tight loop, like you're waiting for a pin to go high for a return for a sonar ping or something like that. So I test the pin, it's not ready, so I call defer. That means I'm going to loop around that. Everybody gets a chance to execute. I'm not holding up anybody, but I'm not waiting either. As soon as I get back, I test that pin again. And that pin will be at that idle rate. But for the most part, you don't call defer directly. So what you do call is you can suspend either to wait on a timer tick or to wait on a semaphore. A semaphore is just a flag that the task can use to synchronize together. The command to wait on a timer tick, we say wake after, and then you give it a number of milliseconds. So we've already seen that in the flash the LED example. We said wake after 500 milliseconds. What that actually does is it suspends the task. That is, the task, this is more like the interrupt function. The task doesn't run at all until its timer tick has expired, and then it runs. So it's not like it's testing every time around the loop and saying, oh, I'm not supposed to run. The operating system takes care of that. There's a macro called period, which also calls that wake after. And what it does essentially, if you just delay, you're not taking into account your execution time. So I did some execution and then I said delay for 500 milliseconds. When I run again, where I'm going to run again is 500 milliseconds plus however long my execution time was. So if you really need to run it exactly 500 milliseconds, you need to know how long your execution time was. And that's what period does for you. It figures out your execution time and calls delay with the proper amount of delay. We can look at those macros and see how they work if you're interested. The second group of doing this is to wait on a semaphore. In this implementation, semaphores are pointers to ordinary integers. And those integers are binary semaphores that can have a value of 0 or 1. They can either have a value of 0 or 1. The semaphore is actually the pointer to the integer. So we have our first example here. It's called semaphore obtain. And you hand it a pointer to an integer. That's what the S is in the parentheses there. And the semaphore obtain will set that semaphore equal to 1, set that integer equal to 1, and then suspend the calling task until that integer goes back to 0. Some other task will have to set it back to 0. So once again, the task is not running at all until that semaphore is set. And there's, of course, similarly, there is a semaphore release. Which way am I going? There we go. And which you also had a pointer. And semaphore release actually runs once around the loop linked list, gives everybody who might be waiting on that semaphore a chance to run, and then it sets the semaphore back to 0. So that's pretty simple. The last one is called semaphore obtain timeout, and it's actually a combination between the wait and the semaphore. You say, I want to wait on this semaphore or until 3,000 milliseconds expires, whichever one comes first. If the semaphore is cleared, then it'll return a 0. If the timer times out, it returns a 1. So you can tell whether or not your semaphore timed out. So with that little handful of code, the only other thing we need to know is how you start up the tasks. And you do so with a routine called create task. Create task expects a name for the task that you want to run. And you can run the same task more than once. So you have a unique name for each instantiation of that. And you have to have a pointer to the function, the program that you want to run. And you get to hand in one argument. As I said, that argument could be a pointer if you need more than one argument. And then you have to tell it how much stack size. Each task has its own stack. Turns out they don't need very much. The ones that need a lot are ones that call printf or sprintf or any of their brethren, because they build their strings on the stack. So you might have a task that needed 30 bytes of stack, and then you put in a print statement, all of a sudden it needs 180 bytes of stack. You have to supply enough space on the task. I have found that a simple way to do it is when you first build the thing, just give them a bunch of stack space, and then you can go back and dump it and see how much they're actually using and compress that back down to what's actually needed. When you call create task, it will either return a process ID, it'll assign a process ID to this task, or it'll return -1, which means I couldn't make the task. Something went wrong, I ran out of memory, or you wrote it wrong. So here's an example here. I have a variable I call PID. We're going to say, I want to create a task. We're going to call it a sample. And we have a pointer to the task. We're not passing in any argument, so we just put a 0 there. And then I say min stack, which is defined somewhere else. When your task runs, you have to have a deep enough stack for the task itself and for any interrupts that might run while the task is running. So there's a little bit of guesswork that goes in there. That's why I say you start with a big stack and then you can reduce it. Once you have that process ID, you can kill that process using that ID with a subroutine called kill process. You say kill process and give it the process ID, then it will stop that task running and remove it from the linked list. If you said kill process and you give it your own process ID, then not only does it remove it from the linked list, but it defers to the next task in the list because you're gone. You're not running anymore. And so that's what terminate is. Terminate is just kill process with my own process ID.
Suicide, basically.
Suicide. Kill self. Well, okay. Well, the final thing I have here I want to go over real quick is a simple demo of using that code so you can see how it might be, how you might use it. So we start off here, and we've got a bunch of includes, and I'm going to define some real-time tasks. And the first one I want to define is the one that gives us back that idle time. So you remember the null task has this variable called proc counter that it's bumping every time around the loop. And what null task is going to do is it's going to, the CPU idle task is it's going to run once a second, and it's going to read and zero that counter. So we'll know how many times the counter ticked over. And you notice that it uses the period call down there, so we get exactly 1 second, and it will take into account. And it just bumps that reads that counter and zeros it. Oh, okay. Here's another task. We've already seen this, to flash an LED on and off. The only difference here is that we didn't tell it 500, we just said we'll hand in how long you're supposed to wait. If that number gets really small, say wait 30 milliseconds, wait 10 milliseconds, then you don't see it flashing, but it just controls how bright the LED is. So, which is kind of neat. You're modulating the LED. Okay, well, here's a couple other sample tasks. This one, that one just flashed an LED. This one's going to flash an LED 7 times, and then it's going to suspend on a semaphore and wait for somebody to reset that semaphore. And if you'd like to see what that looks like, this code is actually running on this processor right here. And if you watch that green LED, you see it flash 7 times, and then waits a while, and flashes 7 times. I know that's not as impressive as a robot, but it should be. So what we do here is we defined an integer I, and we count from 1 to 7, flashing the LED on and off using the delay time that was passed in. And then we say, let's obtain a semaphore. We defined one up here. It's just an integer. We named it flash semaphore. So when we say semaphore obtain, that number gets set to 1, and this task gets suspended until some other task resets that semaphore to 0. So we'll do that in the next task. This one, we'll just wait for a while, and we'll release the semaphore. Well, that's what's going on here. I think it waits for like 3 seconds, and then it releases the semaphore, and the semaphore flashes 7 times, and then it waits 3 seconds. Here's a task to periodically print out the name and the process ID. So, I mean, it's just a little nothing task. Here's one that prints out some statistics. Built into the library that does these calls is a print routine that can print the actual queue itself. So you can see the queue itself, and we'll look at that here in a minute. And this is a function. So we'll jump over all that and get down to the important part, which is main, where we start all this stuff up. This doesn't look markedly different from the startup task for NBOT. You have some hardware initialization, whatever you need for your card, and we're going to set this print vector so we can print the stuff that's down in the system. And then we're going to initialize our sys clock. That's our 1 kilohertz sys clock that everybody else uses for their timing. And then we just create each one of those tasks. So we created the idle task. We didn't pass any arguments into it because it always suspends for 1 second. So it doesn't need an argument for us. And we gave it min stack, which I believe on this was 128 bytes. I can't remember. And we started up LED 1 and told it to flash at a rate of 500 milliseconds. We started up LED 2 and told it to flash at a rate of 50 milliseconds. We started up our flasher and told it to run every 3,333 milliseconds. I did that so it would hemiola. And then we have these 2 print tasks. That's the same task, print me task. Started twice, given a different name, and it'll have a different process ID. And since it's printing, it needs more stack. So it's the min stack times 2, just arbitrarily. You run the thing and it crashes, say, all right, times 3. And the last one generates the stats. And then I generally do this on all my code. The last thing that we call is the scheduler. The scheduler launches that null task which essentially starts up multitasking. The null task starts up and it calls defer and we're off to the races. So we never return from scheduler. It never returns. And so I always put a printf after that. Should never get here. You should never ever see that printf. I have seen it before. And what it means is that the scheduler was unable to start up multitasking. So we had over here, where is this? Here it is.
So maybe it'd be helpful to rewrite that as the scheduler was unable to start up, right? Because you might forget when you see that.
Should never get here.
What is that?
It always shocks me. What? Where did that come from? Well, I don't seem to be able to get to it. I was going to show you that this guy is also dumping his, every 5 seconds or so, is dumping all of his statistics, but I can't find it right. So you just have to watch the little flashy lights. And I think I'm very close to being done here. The only other thing I wanted to add is I want to show here. You remember our initial graph that showed the single task with its long delays. We can now look at all the graphs that way. And this is big enough to see. Pump over here. If you look up in the corner, there's our list of tasks and how much time they're taking. And each one is color-coded. And so if we back off a little bit, and just look at a big enough piece of this, that's what each task is doing. So the pink one on the top is that LCD queue. And it's sitting there waiting for somebody to tell him to write. If you jump down to the 4th line, you see this light blue line. That's the GUI, that's the interface. And you can see it's generating some characters and writing them to the queue, and you can see when that happens, the queue suddenly fires up. And it's been hung on a semaphore until that time. These tasks down here are the ones that are actually bouncing the robot. They're the only ones whose timing really, really matters. That must run at exactly 25 hertz. If it doesn't run at 25 hertz, the robot is woogity. So all the rest of those tasks could drift around a little bit. It wouldn't really matter. But if we measured the distance from this rising edge to this rising edge, it would measure exactly 40 milliseconds, which is what we require here. There's not much going on, and this guy says we're only using 18% of the processor cycles. So I set it up beforehand, and I ran one where it was actually seeking on a navigation target. So it's running all the same code here, but it's also running navigation, which is all that floating point stuff that I don't have in hardware. And if we look at that display, and here, let's make that big enough to see. A couple of things jump out. First of all, these things that are 40 milliseconds apart are followed by a whole bunch of stuff. What that is the calculation of the odometry. That's the calculation of our position. And since it has these big sines and cosines and atangents in it, you just go in and stuck in a defer between each one of those. So rather than eating up all that time, most of the time, as you see right here, nobody else wants to run. So it's just like it's running constantly. It goes all the way around the loop, nobody wants to run, so he just continues to execute. But every once in a while, there's some other task that needs to run. Look here, we can see a couple of them. And you see my mouse here? Yeah. So we ran from here to here, and the GUI needed to check to see if any buttons were pressed. So when we deferred, he jumped in there and ran. Then we ran pretty directly for a couple of cycles, and then this battery, no, that's the analog, the digital converter, needed to run, and so it jumped in here in that slot. And same thing, this is the sensor controls, and they needed to run, so they jumped into that slot. This is our arc tangent. There wasn't a good way to break it up, unfortunately. So between this and this, you can see that we now are using almost 50% of the processing cycles. Still, for a 30-year-old processor doing everything that it's doing, we're only using half the cycles. When you put all this on an ARM, we won't be using any. Isn't there an asymptote there?
It'll be fun to see. So, sorry, I supposedly looked at your code and supposedly helped you, which I don't really believe that. Because I'm asking this question. I think I found some compiler weirdness or something. But anyway, so is the granularity of your timers here, is it all tied to that 1 millisecond?
It's a very good question.
Or is it a fine
Very good
resolution?
question.
Okay.
There's actually 2 clocks running.
Okay.
There's what I call a sample clock, which runs at a higher rate than the sys clock. The sample clock on here runs at 8 kilohertz. It's worse than that, 8192. Okay, so the finest resolution for the logger is 128 microseconds.
Okay,
On the AVR, we got 10 kilohertz
okay.
sample clock, so we got 100 microsecond
Okay.
resolution there. It's a little bit.
There's no reason, though, you couldn't tap into, like, on the AVR, and it's
Exactly.
probably running a 1 megahertz or 6, whatever it is. You could get a fine grain timer if you
Exactly.
wanted.
Well,
What that
actually on
really-
the Arduino, it's running a microsecond one that has a 4 microsecond resolution.
Yeah.
So you can
okay.
call that.
Okay, so I
So
suspect
you
that's
get more
available.
It's
resolution.
a long, so it's a 24.
Okay, great. Okay, so that would be.
Well, what
not-
that really means is that if it's 128 on this display, if it's 128 microseconds or less, it looks like 128 microseconds. I can't log anything any smaller than that. Every once in a while, you'll see, like here, where you just, there's no gap in there. And what happened there was that this ran, nobody else needed to run immediately. So that was less, less than half of 128 microseconds looks like 0. But you're exactly right. Part of the problem there becomes, when you're trying to log what the processor is doing, you're using the processor to do the logging. So, sometimes it gets complicated. If you get the logging functions to work, on the multitasker I have here, every time you call defer, there's actually a macro called yield. Who was talking about yield originally? When you call yield, the difference between yield and defer is yield logs the call. So it sticks the timer and whether you're entering or exiting defer. And that's what these logs are made from. But you can do other things. Once you set up the log, you can do other things. One of the problems, and Dave and I have looked at this, Dave pretty extensively, on these processors, I've got 512K of RAM, so I got lots of room to set up a log. On this one, we got 8K. So we're probably using all of it, no room left over for a log. Dave, however, pointed out that the USB port on this will run as high as 250 meg. So we could run that logger in real time and not need, and he's been working on this, and not need the actual internal logging. Another
Yeah.
option is you could log it to
UART. SD card.
SD card, which would be another way to do it. If you get the logging working, then there's other cool things you can do. And just to tease that a little bit, I will show, here is a log. Oh, come on. Is it there? Yes. This is a log, not of the operating system, but of the balance algorithm. So once you have the log set up, you can stick anything in there you want. So every time that motor command is called that balances the robot, I log all the functions associated with that. So if you look at this here, this big red line is the tilt angle. So what we're seeing here is the robot doing this. Coming to stabilization, finding its stable point. So we start with it way bent over. And these are all the arguments and all the parameters that go into balancing the robot. My favorite one is this light blue one down here. That light blue one conceptually represents what you would do with your body if you were sitting on that robot trying to balance it through that sequence. And you can see we're tipped way forward, so the first thing you do is you'd lean back. But as it began coming toward you, you'd start leaning forward. And you'd lean just a little past center to bring it to a stop. So that's sort of like conceptually what the weight, the center of gravity of weight of the robot would be doing. So there's lots of things like that that you, once you get the logger set up, that are separate and distinct from the operating system itself. I think with that, we are hopeful, Scott and I, that we will have this code actually up on the DPRG GitHub site real soon. In the meantime, I have here in my hand a box of thumb drives, which anyone in this room, if you're interested in playing with this code, you're welcome to take away and play with. I've got 10 thumb drives here. If you've got a laptop, you might just copy it and hand it to someone else. But so this is your free gift. You get this and pizza. And I believe with that, I think with that I'm done. If there's any questions.
So the navigation, when you talk about that navigation routine, that's That's calculating where you've been. It's not planning and where you want to go.
There's, is this the right one? Yeah, there's two things running here. The odometry is what's running here, and all that's doing is keeping track of my current location. The navigation is actually running in this task.
Ah.
So what he's doing is saying, I've got a particular waypoint I'm trying to get to, and this tells me where I am. So knowing where I want to go and where I am, I know how to maneuver. And of course, all the others are running, the pings and everything are running at the same time, so.
So would you
you're-
describe the odometry as being a virtual sensor?
Yes, exactly right. And the odometry, you remember when I had my levels, the odometry I think of as a high-level sensor. It's not actually a behavior, it's just telling the behaviors where I am. And there, there's better ways to do that now. I shouldn't say better. There are other ways to do that. Doug, I think I'm done.
Okay.